Okay, so hi. My name is Shaham, and I really want to first thank the others. I'm learning so much today, so thank you. Second, thank you all for staying sharp up to this time of day. And I'm really glad to be the one between you and your meal. So let me start. I'm going to talk about noble gas spins and hybrid system of noble gas spins and alkali vapor, and present you measurement of the strong coupling regime between the two, and how we can utilize the strong coupling to generate a quantum interface to noble gas spins. So first, before going into details, I'll benefit from other people like Daniel before me that talked about noble gas spins, and say how awesome of a system it is. The record lifetime for helium-3 polarization exceeds a month, and the record coherence time exceeds 2 days. And a given apparatus could contain more than 10 to the 21 atoms. So this is a huge quantum resource that we can use for a lot of applications, like ultra-sensitive magnetometry or medical applications. And here I want to suggest using quantum optics with noble gas spins. And all of these applications could benefit from the strong coupling regime, or even be manifested using the strong coupling regime. Okay, so what I'm going to talk about is first shortly present noble gas spins, and then talk about the collisional coupling between noble gas spins and alkali vapor, and then demonstrate at least to my knowledge, a first demonstration of strong coupling between the two spin species, and how we can use this regime to generate a quantum interface to noble gas spins, and if time allows, which frankly probably not, then I'm also going to talk about applications. Okay, so noble gas spins are odd isotopes of noble gases that has odd number of nucleons in the nucleus, so they have a non-vanishing nuclear spin. For example, helium-3 and xenon-189 that are both spin 1/2. And as I shortly stated before, in these kind of atoms, the nucleus is protected by electrons in closed electronic shells, which highly isolates the nucleus from the environment, and specifically the spin state of the nucleus from the environment. And therefore, these systems present unprecedented lifetimes, like I said before, months and days for helium-3. But this isolation is actually a mixed blessing because it renders these atoms extremely hard to manipulate, prepare, and read out. For example, optical transitions for noble gases start from the extreme UV regime and goes further up. So in order to approach these systems, we commonly couple the noble gas spins with alkali vapor. And in typical apparatus, we have from 10 to the 16 to 10 to the 21 noble gas spins. And the coupling with the alkali vapor generates an interface to the noble gas spins that we can use both to hyperpolarize the noble gas spins to very high percentage, and use in situ magnetometry to measure the state of the noble gases. Here, for example, we see the spin exchange optical pumping process for polarizing the helium-3 in the cell I'm going to present. And we can see that on the course of hours, we reach significant polarizations. So different applications include ultra-sensitive magnetometers, for example, as done by the Hale group here at Mainz. And Peter mentioned Ernst. And as far, if I'm not mistaken, Ernst is also written on this paper from 2010, where the Mainz group measured 100 zeptotesla, if I'm not mistaken, field. And I didn't even know zepto was a number before reading this. So these are highly sensitive. And there are applications such as quantum sensors, and the hyperpolarized inert gases can be used for MRI of the lungs, and measurement or searches for physics beyond the standard model are practiced, for example, by the Romales group. And we, for the first time, I think, suggest to practice these noble gases in quantum optics. Okay, so the interaction between alkali vapor, alkali atoms, and noble gas atoms occurs during collisions, which are thermal and occur all the time. And these collisions are extremely short, from the scale of a picosecond approximately. And during the collision, the wave function of the valence electron of the alkali overlaps the noble gas nucleus. And during this overlap, there's a small hyperfine coupling between the two spin species, between the two spin entities. It generates a small precession between the two colliding spins. And for helium-3, this precession angle is measured by microradians. So these are the dynamics for single colliding atoms. And we may ask ourselves, what happens to the ensemble during these collisions? Well, this question was answered by William Happer and many others. And here I present the dynamics for the noble gas species. I present the Bloch equations, but a similar equation exists for the alkali vapor. And we can see here two significant contributions. So the first contribution is a small second-order incoherent term that transfers spin from the alkali vapor to the noble gas. And this term is used for spin exchange optical pumping. When we optically pump the alkali vapor, some of the spin transfers to the noble gas. And on the course of hours, it polarizes the noble gas. And there's also a first-order coherent term that generates precessions between the two macroscopic magnetizations. And of course, there are also additional Hamiltonian terms, such as the regular Larmor precession. And for the rest of my talk, I'm going to ignore this term, after, of course, polarizing the nuclear spin, because our experiments are significantly shorter than the hours taken to polarize the spin. When we formulate the same equations for ensembles which are highly polarized along the z direction, and we observe small transverse spin excitations, then the dynamics is described as shown here. Now we're going to neglect the decoherence of the noble gas, and we are remained with two types of contribution. Diagonal contributions, which cause Larmor precession of the transverse excitations, and off-diagonal spin exchange, which transfers excitation from one species to the other. Now, if the off-diagonal terms here are a bit hard to analyze because the process is highly non-symmetric. The noble gas density is significantly higher than that of the alkali vapor. So to obtain a better, easier to understand symmetric dynamics, we can transfer our equation using bosonic excitation operators. And before I'll do so, I'll just give you some intuition what these operators mean. So inspired by works of Eugene Polsik and others, we may observe a highly polarized spin ensemble, for example, fully polarized spin ensemble. And now if we observe the state of a small transverse spin, then a measurement would indicate that it is 0, but it still has some non-vanishing variance due to atom projection noise. And if we provide the vapor with a Fock excitation, a single excitation shared among all spins, then the transverse component is still 0, but its magnitude, its variance, is increased. And we can also do that with more Fock excitations. And we can describe the transverse spin component state using the bosonic operator A. And this operator actually counts excitations in the transverse direction. And it upholds bosonic excitations for highly polarized ensemble. And for fully polarized ensemble, we can provide the ensemble with a transverse coherent excitation, which indicates a small angle between the ensemble and the original polarization direction. And that coherent excitation is characterized by a non-vanishing value of A. So when we formulate the equations before, for A and B, we find the canonical beam splitter form, which is much, much simpler. And it is characterized by 3 scales: delta, gamma, and J. Gamma is the dephasing rate of the alkali vapor. Delta is the magnetic detuning between the two spin species. For example, when delta is non-zero, then each of the species processes at its own frequency. And when it is zero, then in the rotating frame, the two species point in the same direction. And there's also a coherent exchange rate, which is, we identify it here, and it is proportional to the square root of the product of the magnetizations of the two ensembles. When we study the dynamics under this effective Hamiltonian, we can identify three regimes. The first is the decoupled or detuned regime, where if we provide the alkali spin with a coherent excitation, then this excitations evolve through time independently of the noble gas. And if we count the excitations, then this excitation simply decay with a rate gamma. And it doesn't feel the noble spin at all. When we bring the system to a resonance by setting delta to 0, which was actually coined by Michael Romelis and Tom Kornack as the compensation point, then in this compensation point, the two spin species hybridize, and giving an initial excitation to the alkali vapor also excites the noble gas spins. But when J is larger than the decay rate, we expect a coherent regime where an initial excitation on the alkali spin would coherently transfer back and forth between the two spin species. And we can introduce excitation to the noble gas spins. And if we turn on the detuning at the right time, we can store this excitation on the noble gas species. Now, the first two regimes were measured by Michael Romelis and Tom Kornack. And here I'm going to show you a first measurement of the coherent regime where strong coupling occurs. So how was the experiment done? We take our vapor cell, which contains both alkali vapor and noble gas spins, and we optically pump the alkali vapor, which is potassium, and let it polarize the helium-3 by spin exchange optical pumping. And after polarizing the two ensembles, we have a vapor cell with high magnetization of the two species, and we apply a magnetic field bringing the two species to a resonance at the compensation point. And we measure the transverse spin component of the alkali vapor using Faraday rotation of an optical probe. If the system is in the strong coupling regime, then when we provide an initial magnetic coherent excitation to the alkali vapor, then it will transfer back and forth between the two spin species coherently. And that is what we're interested in. And to obtain this regime, we need high magnetizations of the two spin species. So we have a high quality vapor cell with a high noble gas density, approximately 3 atmospheres, and long noble gas lifetime, exceeding an hour. The coherence time exceeds an hour, which enables a high magnetization of the noble gas species, the helium-3. We also heat our vapor cell to a relatively high vapor temperature to obtain a high density of the potassium. And we optically pump our apparatus with a significant optical pumping power to obtain a high magnetization of the two species. Here is the apparatus in the lab. Here is the optics of the measurement. And the vapor cell is inside the oven, which is inside the magnetic shielding. Now, we do the experiment I just described, and we provide the alkali vapor with coherent excitations in the X and in the Y direction, which enables us to measure S minus. And we take the Fourier transform of S minus for different values of the detuning. And we can see here the spectrum map measured for these excitations. And here is a model, a simulation for these dynamics with 0 fitting parameters. There are calibrations. I have measured like the polarization of the alkali vapor beforehand. But other than that, there are 0 fitting parameters here. And we can see here in the measurement that we have an avoided crossing. And this avoided crossing indicates the strong coupling regime between the two spin species, where we have our coupling rate greater than 10 times the decay rate of the vapor. Okay, so what have I showed you so far? What I've showed you is that we take two gaseous entities, we polarize them, we let them perform thermal collisions between the two spin species. And I remind you, thermal, these are what we're taught at our undergrad studies as the toy model for stochasticity and randomness and all of that bad words. And by accumulating many, many thermal collisions, the coherent excitation placed on one spin species coherently transfers back and forth between the two spin species. And I found it quite amazing. Now the question is, would the coherent quantum state that was transferred between the two species, would it also operate similarly for a non-classical state, for states with intricate statistics between the atoms in the collective state? Or in other words, could it be done on an operator level? Could it support quantum optics? And to attend to this question, we performed Schrodinger many-body stochastic simulations. We built a quantum state composed of 10,000 spins, and we have alkali spins and noble gas spin. And at each time step of the simulation, we take each of the alkali spin, and for each of the alkali spin, we draw a random nuclear spin partner, and we perform a collision between the two with a random collision phase phi. And we repeat this process for all of the alkali atoms and many, many times. And when we provide the alkali vapor with a spin excitation, we see that on shorter timescales, we have stochastic dynamics, which is mostly noisy. However, when our initial excitation, I can use this. When our initial excitation is placed on a single alkali spin, or when it's placed collectively in a Fock state among all alkali spins, we get very, very different dynamics when we evolve the system through time. For a single alkali spin, we actually simulate and realize the dynamics of spin exchange optical pumping, transferring incoherently the excitation from the alkali spin to the noble gas. However, for a Fock state on the alkali, when we measure the fidelity, in the simulation of course, of the Fock state of the noble gases, we see that the excitation coherently transfers between the two. And when we take more realistic numbers, then the spin exchange optical pumping becomes much, much longer, while the coherent dynamics is still kept. And to really attend to the question of whether this process is non-classical, we simulated a similar system with an initial Fock excitation on the alkali spin and also an initial Fock excitation on the noble gas spins. And we let these two excitations evolve through time. And what we see is that for the realistic number, for helium-3, for example, the number of excitations, when we count them in the simulation, the number of excitations on each spin species remains constant, relatively constant, while the fidelity for the quantum states, we see a periodic bunching and anti-bunching of the excitation on the spin species. So this is actually a realization of the Hongo-Mandel effect, which is non-classical by any standard. On the next stage, we wrote a detailed analytical model for this process. And this detailed analytical model enables us to derive expectation for experiments. And it actually shows that any non-classical state placed on the alkali vapor would transfer to the nuclear spin and back. And it enables us to identify on what conditions would the transfer work and when would it stop and break. Okay, so I have here several applications. And as I expected, I don't have time to talk about. So please, 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 if you want to hear about suppression of projection noise in gas magnetometers and about schemes of quantum optics using noble gas vapor, please come visit me at my poster, which is a 5.5. And it is right behind this wall. So actually, this picture is funny twice. Okay, let me just summarize what I told you. So I showed you a measurement of the strong coupling between noble gas and alkali vapor spin ensembles, and that this measurement is quite unique because it's generated by accumulation of random collisions and thermal collisions. And I showed you that this strong coupling could actually generate a quantum interface to the noble gas spins. And I didn't have the time to show you, but if you come visit me at my poster, I'll tell you how we can use this quantum interface for quantum optics or for improved magnetometry, suppression of fundamental projection noise with our noble gas spins. And while you ask me questions, I'll just leave this movie of us making our, fabricating our vapor cell for the xenon experiment. Thank you.